Okay, I think we're all here. I'm here. I don't know how it looks like there are 10 or 5, depends on how it counts, of you here. These will be recorded though, so are they being recorded as we do them, and they'll stay up indefinitely as far as I'm concerned until YouTube takes them down. So you can come back to them at any time and watch them later, or watch them for the first time if you have to watch them later. But so this is actually the third lecture in Engineering 220. The first two were one on 2D concurrent force systems, and the second one mostly on 3D concurrent force systems. So those were kind of getting you started, maybe on the static side of things. So this course is statics and strength of materials, and so that first little bit was basically pure statics. Today we're going to enter into some of the strength of materials type of things. I do have the chat going. I will look at it, as I can. There's a pretty significant delay between when you type something and I actually see it, so don't get too alarmed if I don't respond right away, because it does take, I think we're maybe off by 20 seconds even between when I say something and it actually shows up out there. So don't be too worried, but if you have a question or a particular thing you want to ask, you can put it in the chat. We also have the Discord channel. I saw a couple of you join that. You can ask questions in there. Not during the, you can ask during the live stream, but I'm not looking at it during the live stream. Maybe I can figure out how to do that sometime, but for now, that'll be kind of offline type of thing. You can send emails. We can set up Zoom meetings if you need something more like direct, not just an email type of response. But today what we're going to do is we're going to look over here. This is in Canvas. So like I was saying, class 1 and 2 you should have already done. Those, well, maybe 1 for sure should be review. 2, you may not have done any 3D concurrent force system things, but it should be not anything terribly new. You may not have done forces in 3D yet though. Today is stuff that you probably have not done unless you've had some other strength of materials course somewhere. So what we'll do today is we'll start looking at the combination of statics. So the idea that we have forces applied to objects. The static part of it means that we're not really dealing with dynamic situations where things are flying around and moving and all that kind of stuff. We're really just looking at static forces that are applied to objects, and then those objects respond by deforming or breaking, or they have some sort of response that's a mechanical response to this thing, but it's not that they're moving somewhere. So we'll start that today. The course is generally broken into 3 big categories. The first one is axial forces. So axial meaning that the object has some type of longitudinal axis. It may not be perfectly symmetric about this axis, or it could be, probably our examples will be, but it has a longitudinal type of axis, and forces are applied along that axis. Generally, they're either making it compress, so they're pushing on it, or they're making it elongate, they're stretching it out. Those are the 2 general categories for axial stress. We'll do that for 2 or 3 weeks, and then we'll go into flexural stress. So now maybe we've got an object. I'm looking for an object. Well, I've got this. So we've got this. Let's get the closer up version. Got this, and instead of just pulling on something trying to stretch it out, we're flexing it, bending it one way or another. And so we'll have a new kind of force, same kind of force actually that we've been dealing with, just it's doing a different thing. And then we'll do that for 2 or 3 weeks, and then the end will be an assortment of things, including the third type of stress, which is going to be a torsional stress. So things are twisting. If I had I'm twisting it one way or another, and that's a different response. In this course, we won't combine those 3 things together. That is certainly possible that you're pulling on something, bending it, and twisting it all at the same time. That's for another course. That would be the follow-on course to this, or one of the follow-on courses to this. So we're that's the general structure of the course. We take an exam after each one of those big categories. The final exam definitely covers all of the things, but they kind of build on each other anyway. So it's not like these things are independent. We just don't combine them together into one really complicated load scenario. So today we're going to do this axial stress. You should also be aware that as we go, you're getting like here, homework 3. So all of those are in WebWork. So you have to log into WebWork and you go and you do your homework over there. In general, we talk about something, the WebWork opens up, and then you have a week to finish the WebWork. That's generally how it works. It's not going to be perfectly exactly like that every time. Sometimes you'll get a little longer depending on how maybe it's there's something else going on that week or whatever. But in general, that's how it works. So why don't we just jump into the idea here of stress. So I have got let's go to this and over here. So we're going to give stress a word definition first, and then a generic formula definition, and then I think maybe 3 specific formula definitions. So stress, let me make sure I'm not too far off of there we go, coming back. Stress in general. So stress is the intensity of, and then here's an important word, internal forces. So we have all these external forces like the ones we did in the first lecture and the section lecture. Those are kind of acting on this object. You know, we really didn't say what it did to it, but they were forces, and we were balancing forces and things like that, or maybe finding resultants or finding components. All of those forces are acting on these objects, and inside the objects is what we're talking about now. So all these external forces do something. They try to stretch out a beam, or they want to compress a column or something like that, and it's the internal forces that we're interested in. So the intensity, how intense are those internal forces, is what we call stress. So that's our general definition of stress. Our general equation for stress is that internal force divided by some I'm going to say cross-sectional area. So that's the general definition. We're going to make some specific definitions for different types of stresses in a minute, but that's the general thing. A lot of times we'll say this. Oops, I didn't finish out internal force, did I? A lot of times we'll just simplify this as F being the internal force. Sometimes it'll be P over A. So force over area. That's what stress is there's some kind of force, and it's distributed over some kind of area, and when we find that ratio, that is the stress. And then we've got another term that I'm going to say is strength. And this is how much stress can a object take, a material take. So different objects are made of different materials. It's the material itself that determines how strong it is. So strength is how much stress can a given material endure, we'll say. Endure may not be the best word, but that's a good enough word. So this strength is a material property. And it's a thing that we can find, so we can do some experiments. And so this is a lecture lab. Obviously, when we're online, the lab part has to change a little bit. So we're going to do some simulations later on in the quarter to count as labs, and they'll simulate how you would go and actually do some of this testing and figure out a material property. Now, normally you don't have to go test every material you're going to use. There are charts. In our case, let's see, we've got some charts. Where did I put them? I think I put them in here, maybe? Yeah. So if we go to the General tab in Canvas, there are these reference materials and material properties. There's a material properties PDF. We can look at that and get an idea of some material properties. So let's just look at one of them here, zoom in on it a little bit. So here's some materials. We've got ferrous metals, non-ferrous alloys, non-metallic materials. Those are a little bit different, but we do have some properties there. And then we've got a table with all sorts of numbers in it, and letters even. And then these columns up here are different things, elastic strength and ultimate strength and specific weight and all that sort of thing. This is the type of table where we can go find these material properties. You even see some that are labeled strength. Now there's two of them, so we'll have to talk about why there's two. But there's a strength and there's a number, 30 KSI tension. So that was, we mentioned that when we were pulling on something, we're putting it in tension. And so maybe we've got this generic structural steel here, 36 KSI is its strength. So now at least we have a number that we can try to figure out what that means. So one of the things we need to do is we need to be able to find a material strength, calculate a stress in that material, and then see if it's going to be okay or not. Materials can fail in different ways. They could just straight up break. They could just kind of flex a little bit, stretch a little bit, and so we have all these different properties. I did just see a question in the chat about the quiz. What can we do to prepare for the quizzes? If you notice, we'll take it a little aside and talk about that. Let's see, where would that be? If we go here and notice that there are some quizzes. Let's see, where's one coming up? There's one, quiz one. There are 5 of these. So these quizzes, doing the homework is preparing for them. These are really small quizzes. You do them on your own. They're not like exams where we sit and proctor them or anything. It's just a little test basically of where you're at, and they're meant to be on the simpler side. So you do quiz 1 or in any of the quizzes, and you have about an hour. It shouldn't take that long, but the whole point of those quizzes is that if you're struggling with that content, then you're probably not quite ready for the full-blown exam content. So I would not actually prepare at all for them. I would do the homework, watch the videos, and consider that you're preparing, and then take the quiz and see where you're at. That's kind of how they're 1 point each, 1 or 2 points each, so they're not very heavy on your grade. But do them. Don't leave them out empty. But I would use them as kind of a marker of where you're at. You know, are you doing okay or not? If you should make 85s and higher on these quizzes, and that doesn't necessarily mean you're good to go, but it means that you're on track at least, and you're not way behind on something. So I actually wouldn't prepare for the quizzes other than making sure I did all the homework and I was up to speed on the lectures. That's how I would prepare for those. All right, so back to our stress and strength idea. All right, so in the stress category, there are multiple kinds of stress that we might have. The first one we're going to talk about is, I'm going to move the, oops, I'm not going to do that. Get that out of there. I'm going to move these. These are for later. We're going to move them down out of our way for now. All right. So the first stress we're going to talk about is still under the axial. We're still under the axial category. So our big category is axial. And then underneath axial, we have the idea of stress and strength. And now we're about to talk about a specific axial stress. So we're going to talk about a normal stress. Sometimes People just call this one axial stress also, but we're going to specifically call it a normal stress. And this normal doesn't mean average or, you know, ordinary. This normal is perpendicular is what it's referring to. In that sense of the word normal. And we're going to give it a specific equation. We're going to say sigma, that's my version of the Greek letter sigma, equals, and then you might see a P or an F. I'm just going to use F over A. So that's going to be our equation that tells us we're doing a normal stress. So let's take a really straightforward example to start with, and let's just put a rectangular piece of metal, like a bar, under a tensile load and calculate the stress on that thing. So this is about as simple as you can do. So here's I'm going to try to draw these in 3D so that you're not looking at just rectangles, but you have some sense of their actual objects. But here's what I'm going to draw. So there's our little rectangular bar. I'll try to keep things more or less color coded so that the black lines are the object, red lines are usually forces, and then green lines are coordinate systems and dimensions and stuff like that. So this, actually let's make that a little bigger, thicker. There we go. There and there. Those are our forces. So this is an axial force. This thing has a longitudinal axis. It kind of lines up right with that line, doesn't it? So we kind of have to dip down a little bit. But there's a longitudinal axis here. And this force is on that axis, kind of stretching out this bar that we've made. So this is a tensile force. Because it puts the object in tension, meaning that it's stretching it out. You can also tell tensile forces because they point away from the object. So if they point towards the object, they're compressive. Away from it, they're tensile. Let's give it a value. Let's say that this thing is, I don't know. Let's use a relatively large force, 500 pounds. Now I'm going to have to put 500 pounds on both ends here. If you go back to some of the stuff from lecture 1 or 2, remember we had the idea that the forces had to balance. They had to be in equilibrium, static equilibrium. And if I don't put, maybe I don't put this 500 pounds on the right-hand side, this is not in equilibrium. I've got 500 pounds going to the left of, you know, on this little bar trying to pull it to the left. And I've got, I don't know, let's just say it's 0 pounds trying to pull it to the right. Well, it's going to move to the left, and now we're not in statics anymore. So I have to have an equal and opposite force and reaction. So I've got one of these can be thought of as the force, and the other one can be thought of as the reaction. Now, one thing that confuses people here, though, is that they think that, oh, I've got 500 pulling one way, 500 pulling the other way. The inside of this must be under 1,000 pounds. Because remember, we want internal forces on our stress equations. But now this is going to be overly simple to do it in this case, but it does help you later on. If you can do it when it's simple, then you can gradually build up to the more complex stuff. But I'm going to take, and I'm going to, you know, I don't know if that showed up very well. Let me see if I can make that a little bit bigger. There we go. I'm going to cut through the middle of this bar because I want to see the inside, right? I want to see the internal force, so I want to see what's inside it. So I'm going to cut it open. I'm going to pick one side or the other. It doesn't matter. Actually, let's just do both of them. I'm going to draw the left-hand side, and I'm going to draw the right-hand side, but cut open. So here's the left-hand side. It's something like this, and then the right hand side, you know, it's kind of got a matching jaggedy area. Now I am drawing these kind of jaggedy, but we are making some assumptions that everything breaks perfectly smoothly and all that. That's not real. That's not the real world, but this is our first introduction to this stuff, so we're not going to try and figure out exactly how things look when they break, you know, how jagged or what angle did they break at. We're just going to assume they broke perfectly straight, even though I draw it kind of jagged. All right, so here's the situation on this piece. Here's the situation on this piece. Now, once they're broken, they fly apart. But right up until the point that they're broken is what I'm interested in. Or we know, I don't know, this might 500 pounds might break it, it might not, I don't know. But when we look at this, I need to move them further apart. Let's move this guy over there. So inside the left-hand piece, there was some kind of reaction force inside there, and up until the point of it coming apart, that reaction was 500 pounds, so that piece was in equilibrium. And the same thing over here. So the internal force, no matter which side I look at the left-hand side or look at the right-hand side, the internal force is only 500 pounds. It's not 1,000 pounds. So that's a part that confuses people. I mean, it's really simple to get once you get it, but your intuition tells you it's 1,000 pounds because you're pulling two different directions with 500 pounds. But you're not really doing that. One of these is the force you're applying, and the other one is the reaction to that. So it doesn't matter which one. We'll just say that's the applied force, and this is the reaction to that applied force. So it's really the same force. It's just there's something somewhere holding this bar steel. There's a bolt or a weld or glue, I don't know, but there's something on the other end that's holding this bar in place, and then I'm pulling with it with 500 pounds. It's not that I'm pulling in both directions with 500 pounds, although that's what it would look like if I drew our diagram here. So that is actually an important word there. So what I'm doing here is I'm drawing free body diagrams. Whoops, that should be an R. So free body, meaning that the body of interest is floating out in space. So it's free from everything else. And that I have applied all of the forces that are acting on this body. Now, here I've got two little bodies that are, it's just a piece of the whole bar. But that's okay. You can have free body diagrams that are a single item, like this pin. Or you could have free body diagrams that are just a piece of this pin. You take it apart and it's just the piece of it. Or you could have free body diagrams that are of a really complex assembly. So there are a lot of different ways to do free body diagrams, but they are going to be the most important part for statics and strength of materials. So just like a circuit diagram for circuits or a control volume for thermo or something like that, every kind of discipline of engineering has its diagram or its picture with its own rules of how you create that thing that helps you solve those problems. So for statics and strength of materials, it's the free body diagram. So you've got to get in practice drawing free body diagrams. And the easiest, even though this is kind of silly to draw because it's just this little rectangle, it's good practice to start learning how to correctly assemble your free body diagrams. So that you can actually solve the problem correctly. So I would look at this, and I would not need to draw this as a free body diagram necessarily because it's so simple, but it is good practice to start with the simple stuff. If you can't do the simple ones, then you need practice on them before you can do the more complicated ones. So I'm trying to do this stress. So I want to do a perpendicular stress. So the perpendicular here is talking about the fact that the force is perpendicular, so there's my little perpendicular symbol, to the area. So the force here is perpendicular to the area here. So if I look at my diagrams here, the internal force, let's just do the right hand side. So there's the internal force. The area that it's perpendicular to is this little area. That's the area that it's acting on, and it's perpendicular to that area. And so since the force and the area that I'm looking at are perpendicular, then this tells me it's a normal force. And so then I can use normal stresses and normal strengths and that sort of thing. In order to calculate this, I need some dimensions. So let's put, I don't have a great place to put the dimensions, but let's put them here. And let's just say that that distance was, I did pounds, so let's do some kind of inches here. Let's make that a 1/4 of an inch. And then let's do this distance, which is really going to get convoluted in there. Let's say that that one is a 1/2 inch. Okay. And even though I drew the bar a little bit wavy, we'll assume that it's perfectly straight, you know, and it's not, everything's the same dimensions. So if I want to do this calculation for sigma equals F over A. The internal force is 500 pounds. And I'm looking at that internal force. And the cross-sectional area is whatever the area of that little green hatched piece, which is, it's a rectangle, 0.5 inches times 0.25 inches. So I had a calculator somewhere. Here it is. No, that's not it. I don't know where I put it. I may not have brought it in here. Okay. We'll have to get the old phone calculator, I guess. Let's see. Here we go. So 500 pounds divided by 0.5 times 0.25. 4,000. And the units on that are, I've got pounds in the numerator and inches squared in the denominator. So pounds per inch squared. A lot of times we won't say pounds per inch squared. We will say 4,000 psi. Now, you have probably heard psi in terms of like air pressure in a basketball or something like that. But it's also the same units for stress. We have this weird unit also that combines the metric system and the US system, and we have 4.0 KSI. So they took the K from kilo and combined it with the PSI from pounds per square inch and gave you 4 KSI. So a KSI, 1 KSI equals 1,000 pounds per square inch. So that's just a little, if you haven't seen that unit before. We have another one that's related to that, that sometimes the forces that we're having to deal with on these kind of beams, you know, these beams can be really large. The one that we're dealing with here isn't very big, but they could be really large. We do have 1 kip is equal to 1,000 pounds. So we do have that as a potential unit too. We didn't use it here, but sometimes you have to put, you know, 40,000 pounds on a beam because it's part of a bridge or whatever. And instead of writing 40,000 pounds, you write 40 kip. So just be aware of these little kind of oddball units that you may not have seen before, where they combine the K from kilo and the US system. All right. So that was pretty simple. So we ended up with 4,000 PSI. What we could do then is we could go look at our web page, material properties, maybe our structural steel, And it looks like this thing, well, let's look at ultimate. That's probably easier to understand right now. Ultimate strength, the point at which this thing would break, is 66, and the units there are KSI. So it would take 66,000 pounds per square inch to break a piece of structural steel. If this thing is structural steel, if this little bar is structural steel, even at this pretty small dimension, 1/2 an inch by 1/4 inch, we're nowhere near breaking it. In fact, let's move these guys down again because they're getting in the way again. In fact, we could say that we have a factor of safety against ultimate failure would be like fracture. So FS, that's going to be factor of safety. Is going to equal what's your strength divided by your stress. So how much can you take divided by how much do you have? So our strength, if we were doing the structural steel, ultimate strength was 66,000 psi, and we only have what was it, 4,000 psi. So what's that number? 66,000 divided by 4,000 is 16.5. So what we would say in this situation is that we have a factor of safety against fracture because this number was the ultimate strength. Some people would call that the fracture strength. Your book calls it ultimate strength though. So we have a factor of safety of 16.5 against fracture. And that's a really high factor of safety. So normally the factors of safety that we're trying to operate with might be like 2 or 2.5 or something like that, or maybe 1.5 in some cases. So 16.5 is a very high factor of safety. Okay, so I'm looking at the chat. I don't see any new questions over there, but if you have questions about this stuff, go ahead and ask them. It'll take me a while to see them and answer them, but go ahead and put them in the chat so that I don't miss something. We don't have to go too far back to catch up to it. But this is our example, super simple example for normal stress. Okay, and some people would just call it axial stress. Although I'm using axial stress as a bigger category, and normal stress is a particular type of axial stress. All right, I don't see any new questions over there. We'll keep an eye on it, but I don't see any. Let's move on to our second type of stress under the axial stress category. So this one I'm going to call, let's move these down some more because we need some new space. I'm going to call this one shear stress. Okay. Okay, so it's still an axial stress, but it's not perpendicular. It's not normal stress. So the force in the area the force is acting on they're not perpendicular to one another. And it's shear, S-E-A-R, not E-E-R. So shear stress. So there's actually an example of it in this picture. Maybe I should get it back. So in this picture, maybe make it a little bigger. In this picture, you've got this little safety pin right here. It actually might be a U-shaped pin, and now that I look at it, I'm not really sure. But you know, this is a jack stand of some sort. You lift up the car, put this thing in place, and it's got some adjustment in it. You can turn this to have a fine adjustment, but you also have these holes where you can raise it up in, looks like an inch increment at a time. In order to keep it from just falling down, they've got this pin that goes through this green part, through the gray part, and out the back side, and it is in shear. So if we were to take, let's just assume it looks like this is a U shape, like there might be two pins that go through here, through these holes. But let's draw kind of what that might look like, and then we'll use that to talk about shear stress. So I'm not going to draw it in this view. I'm going to draw it looking from this direction. So if my, eye is over here, oops, I'm kind of looking at it from that side. So that would look something like this. There's the outside of the green part, and then the green is pretty thick metal, so we'll draw the thickness of it kind of like this. And I even have a green, so we'll make that kind of green in there. Okay, so I'm kind of just drawing maybe that little section right there. Now inside the green square tube is a gray square tube. So we're going to draw that one kind of like this. We don't really know how far down it goes, so I'm going to end it right there. So that'll be its bottom. These are just kind of, I don't know how far they go. It, I think, is also a tube. So we will give it a little wall thickness here. Maybe it's thinner than the green, I don't know. Might be the exact same material. And I don't really have a gray, do I? Let's see if I can. Yeah, there's a gray. All right. So there's the gray tube. And then this pin, this U-shaped pin, goes through all of this stuff. So the pin goes through here, all of this, and then it's a U shape, so it does something like this, and it goes through all of this. So that pin is in what we would call shear. So this pin is in shear. In fact, you might even call this a shear pin sometimes. And what that means is that obviously, if I've got a car sitting on this thing, there's a pretty big force up here, right? So there's a force that's being applied, ends up being applied to this gray tube. And then there's the reaction force over here because the green thing is attached to a bunch of stuff that's sitting on the ground. So I did put 4 arrows here, kind of split it apart. But let's just say that our car, that this corner of the car that it's lifting up or holding is 800 pounds. That's kind of realistic for a smallish car. If one quarter of it is on this thing. So let's just put 800 pounds total, which would put 400 pounds here. And I'm going to assume that it gets evenly distributed. So this is a sophomore 200 level class, and so we're going to generally assume things are evenly balanced and symmetric and all that kind of stuff, at least for now. Now someday in the future, another class, another course, you might have reason to think that this 800 pounds does not get evenly spread across the two sides of the gray tube. I think it would, even in most more advanced ways of looking at this. Those 4, or that 800 total, those two 400 pounds need to be reacted, and I'm just going to put all of the reaction here. Right? So now I've got a thing that's in equilibrium, but the gray and the green aren't actually connected together. So all of this force ends up, I'm going to use a red arrow, it ends up on this little surface, that little surface, that little surface, and that little surface. So if you look at those surfaces, they are not perpendicular to the forces that are causing stress there. In fact, they're parallel to them. And so that's what we mean when we say they're in shear. So now the force is not perpendicular. I used the symbol last time, didn't I? Not perpendicular to the area. In fact, in everything we do, they're going to be parallel. The force and the area are going to be parallel when we're talking about shear. Okay. Parallel to the area. So to distinguish when we're talking about shear versus normal stress, we use a different symbol. So we're going to use tau. That's my Greek letter tau. Equals, and instead of saying V, instead of saying F, we're going to say V. So internal shear force over the area that shear force is acting on. So same idea, force over area, but two big differences. The force is parallel to the area, not perpendicular to it, and let's go over here to our material properties, and let's find one of these that has a list. All right, so shear, here's one right up here. So for that's wrought iron, the very top one up here, the ultimate strength in tension for this wrought iron is 48 KSI. So it's weaker than the steel that we just had, but this is a different material. But the shear is 25 KSI. A lot of these don't even have shear listed. There's a reason for that that we'll briefly discuss here in a second. But we need to definitely make sure that we're treating shear stresses like shear stresses and measuring against shear strengths, because shear strength is way less than the tension compression strength of materials, at least of these type of materials that we're dealing with. So I said a lot of them are missing. Like there's nothing listed over here for the structural steel. That's because there are different models you can use for calculating shear stress based on the tensile strength. We're going to take the super simplest one and the most conservative one and just divide by 2. Unless the number's listed, like here, the tension strength is 48 and the shear strength is 25. But if it's not listed specifically, we're just going to divide by 2. There is a probably more accurate way where instead of multiplying by 0.5 like we're doing, you multiply by 0.577. That's distortion energy, but that's a thing for a future course, not even this course. So we're just going to be really conservative and simple, and say that we're going to take half of the tensile strength. That's going to be our shear strength, unless it's specifically mentioned. Some of these, there's a specific number mentioned, and it's not half of the other number. So we'll use that in the case that there are numbers actually mentioned for shear. But if there's not, we're just going to take half. That's the, what is that, maximum shear stress theory or something. So it's super conservative on estimating shear strength, but it's also easy, and it's easy to remember. I think, let's see. I thought sometimes there's a note down here in the bottom of these charts. This one doesn't really have one, though, about what to do. But you have to choose, because there are multiple models you could use for calculating the shear strength. We're using the most conservative, simplest one. All right. So back over here. Where's there? There we are. If we wanted to calculate the shear stress in these pins, well, this pin, but this one pin would actually need to fail 4 different times, right? All 4 of these little red squiggles that I drew would have to break in order for the jack to fail. So this would actually be an example of quad shear. So you can have single shear, double shear. Here I've got quad. You can have any number. But in this particular case, we would need 4 different cross sections of the same U-shaped pin would have to fail for the jack stand to come crashing down, which, this is a jack stand. We're probably working under this car, so we want it to be not likely that this thing's going to fail. So we've made it have to fail 4 different times, at least for the pin to fail. There are other ways the jack stand could fail. There are even some ways like this where instead of a tensile force, it's a compressive force. Other parts of this do have our normal forces, and it's possible they would fail. But this particular one is a shear stress. So let's try and calculate this shear stress using our shear stress equation over here. So this is sort of a free body diagram. I guess we did, this is close enough to a free body diagram that we can work from here. A lot of times I'll draw what it would look like if it failed, but this one's kind of going to be hard to draw failed. I'll draw these middle pieces. So I'll draw the middle pieces. This is what the failed pieces would look like if we looked at the pin itself, just the pin. So we would have something like this, and another one just like it here. And then our areas that we're talking about are this area, this one, and then, back here in the background, that one. So those 4 green circles are the 4 red squiggles in my diagram at the top of the page here, showing where it would fail. So each of these, we're going to assume that all of our load, our total load is 800 pounds, right, over here. Under the word shear stress, that's our total load. We're going to assume that it gets evenly spread out over these 4 areas, and I'm going to show the reaction to that 800 pounds as these 4 areas. Now, figuring out, well, how much is this really going to be? The total external load, looking over here at the jack stand, the whole jack stand on the left, the total load is 800 pounds. That total load gets spread out over these 4, so each one of these is 200 pounds. Now again, does it get spread completely, perfectly, evenly? It actually gets close, assuming that these are all the same size, because as you apply loads to objects, they kind of, they deform a little bit, and they kind of all even out. So assuming that it's more or less even to begin with, then it's going to be close to each one of these 4 little green circles having about 200 pounds on it. They might be one that's a little bit smaller and it's got a little smaller area and the stress is higher there, but for this course, we're assuming things are perfect. So that's kind of how I would draw this. I would also need to know, what size are these. So I don't know. Looking at the picture, maybe that's 3/8, maybe that diameter. I'm going to use inches since I use pounds on the other thing. We will use both metric and US in this course. A lot of times I end up defaulting to US units, but metric units are just as valid and useful. And so we will use both. Let's see. One other thing about these. Notice this is just a technical thing, but for forces, just the forces we've been using, a regular old force, we've used an arrow kind of like that. But for shear force, we show it differently, and the arrow is only one-sided. So that's another way that we're reinforcing the fact that these particular things are shear forces generating shear stresses. And so you even draw the arrows with only half their arrowhead to show a shear force. Also, super in the weeds here, but I'll go ahead and tell you, this arrowhead size is 3, and I guess this one doesn't have the other side on it, but to 1. So that's really not very important. But if you're drawing these by hand and you want it to look consistent and typical, then the arrow head is 3-to-1 ratio. All right. I'm not going to grade you if your arrowheads are 3-to-1 ratio. All right. So to calculate our shear stress, tau equals V over A. It doesn't matter how we approach this. We can either say that, well, our total force is 800 pounds. You know, we have 4 200-pound shear forces. And our area is 4 areas that are pi times diameter 3/8 of an inch, pi d squared over 4. Let's see, I've got to get my parentheses sorted out right. So you can either do that, or you can just say that, well, they're all equal, so one of them is 200 pounds over a single area that is pi d squared over 4. Also, another aside, you probably often do area of a circle as pi r squared, which is completely fine. I did pi d squared over 4, which is equivalent. Seems more complicated, except that like if you go to actually talk about things that are round, like a bolt or a pin, or if you go to measure something that's round, you know, you get your calipers out and you measure it. You're measuring and you're talking about the diameter. You're not measuring or talking about the radius. So it usually makes more sense and it's more familiar if you use pi d squared over 4, because that's probably the measurement you have. It's totally fine to say, well, the radius is just half of d and deal with it that way, but you're probably going to be given diameters, and that's what we were given here, 3/8 inch diameter. Now my phone calculator is probably not going to like this very well, but let's see if we can calculate this. All right, so our numerator is 800 pounds. Our denominator is 3/8, so 3/8 of an inch squared, which I don't even know where squared is on here, so let's just multiply by 3/8 again. Whoops, 3 divided by 8. So pi d squared times pi, which we're just going to use 3.14159 because I don't know where pi is on this. Divided by 4 times 4, so we don't need that. That's going to end up being the same thing. And I think, let's see, did I get everything squared times pi? All right, so I think our denominator is 0.4418 inches squared. So we do end up with PSI. I'll answer the question in a second here. So 800 divided by 0.4418. So I think, and y'all can check me on this because I'm having to calculate on a phone, not a calculator, 1810.8 psi. So if somebody can say that that's right or not, that'd be great. The question though was up here, why did I draw all these arrows pointing up? So it's because I took a shortcut and I didn't draw everything. So let's take all of this, take all of that and copy it, and then let's put it down here. And let's say that one way that this thing could break is like this, right? Or well, the way we're interested in is that the pin, the U-shaped pin, shears and the thing falls down on us. And so what that would mean is that all of this is gone, right? All of this is gone. The gray inner tube, or well, section, shears off the pins in there inside the jack stand, and this thing comes crashing down. So all of this part crashes down on us, and it goes down inside that green tube. So what that would do is, this is kind of the failure mode. That's the gray tube. It has sheared all of the green, well, no, it's sheared all of these green circles, and the pin, the little pieces of the pin, there's a piece of the pin kind of over here laying on the floor somewhere, and then somewhere over here there's these little pieces, they're laying on the floor somewhere too, or maybe they're stuck in the green tube or whatever, but they're not holding up the jack stand anymore. And so this free body diagram, this would be the free body diagram of that situation. So what if, we're asking what if questions. So what if the pin, the U-shaped pin, failed on us in shear? This is what it would look like. And that free body diagram would be, well, I've got the 800 pounds pushing down. So these shear forces are all of the reactions to that. So if I don't have these 200-pound reactions on each one of those little sections, then it's failed. It's broken, and the jack stand has come crashing down on us. So if I did a simple little, remember from our equilibrium, summation of forces in the y direction equals 0, assuming the y direction is positive going up, then I've got a total of, I've got minus 400, because those are pointing down, that's these two, plus all of these, there's 4 of these 200 pounds. If that does not equal 0, which it does right now, then I'm not in equilibrium and things are moving around on me. So that's why I pointed them up, is that they are reactions to the 800 pounds of the car sitting on top of the jack. So that's why I drew them that way. Now, the good thing about shear is that it doesn't matter if you shear like one direction or the other direction. So the direction of shear arrows doesn't matter as much because the material behaves the same. But for the axial forces, if we go back over here and you look at, let's see, well, look at the cast iron gray. It has one number in tension and a completely different number in compression. So some materials don't behave the same in tension and compression. So it does matter if you get those arrows right. Plus, the part itself may behave differently in tension and compression. Think about a rope. I pull on the rope and it's great, but I push on the rope and it doesn't resist at all. So it does matter when you're talking about non-shear forces, if you got the arrows the right way. But shear forces, if you have the arrows backwards, it behaves the same either way. So it's not as big a deal. All right. So that's that. Oh, let's see our number. So I never saw if this was right or not, but 1800 and psi, or 1.8 ksi if we wanted to use that. Is that a big deal? These are probably steel pins. We can have that generic structural steel number up there. It has 66 ksi of tensile strength. It has no number listed for shear, so our idea is going to be that we're going to take half of the tensile, so 33 ksi. We're at 18. We're at 1.8 ksi. So we're nowhere near failing this thing. So if we wanted to write that out, it would be our factor of safety. And again, we're going to do against, against fracture equals our fracture strength, which your book calls ultimate strength. If this is structural steel, that number is 33 ksi, or 33,000 psi, divided by our stress. in this case, this is a shear. I guess I should be specific that we're talking about a shear fracture here. So our shear stress that I calculated was only like 1,800 psi, assuming I did that right, which I don't know. It was approximately that. So that gives us a really large factor of safety of, if the 1,800 is right, then 33,000 divided by 1,800 something, 1,810 is what it was. But if we did 1,800, it's 18.3, approximately 18.3. So even more factor of safety than the first one we did. Now that is assuming the 1,800 psi is right. You'll have to do those calculations on your own. It's really, just this little equation, which hopefully I did correctly, but on the phone, I don't know. All right. Any other questions on the shear or normal stress? We have one more type of stress, and actually there's another type of shear, some other words, still a shear stress. All right. Oh, wait, there is something. Oh, okay. Somebody said that they got the same number. Good. Then they actually used a calculator. So hopefully that 1810 is right, which gives us a really large factor of safety. Now, this is, I want to point it out again, you do have to make sure you know shear stress from non-shear stress, because the strengths are so different. If we only had a factor of safety of like 1.2, but we actually calculated this as a regular stress and not a shear stress, then it probably would fail, because shear strength is so much less than the tensile and compressive strength. So be careful making sure, and you can 100% know when you draw your free body diagram if the applied load, so in this picture it's easier to see, if the applied load, the 800 pounds up here at the top, or the two 400 pounds, and the reaction loads, so the internal 200 pounds, all these little 200 pounds, if they are not perpendicular to the area you think is that you're interested in at that time. So here the areas are, we're just seeing the side of them, but here, those four areas, it keeps erasing them. It thinks a squiggle I want it to erase. So the if those forces are not perpendicular, then it's a shear force, and you got to do a shear analysis. The equations all look the same, but the strengths are way different. All right. So let's talk about the third type, and then we'll go back and do some special cases for some shear. Actually, the third type we'll use this picture. So let's move it down here. Okay, so another type of jack stand. So here we have some, you could maybe calculate a shear stress on this pin that's going through the bar here when you try to raise the jack up or down. It's act like a screw. There's some normal stress in these legs over here, and in the screw itself there's a big normal stress there that we could calculate. But this one is a special case, and it's going to be called a bearing stress. And it's going to look pretty much exactly like a normal stress, but it's a special case. So we will use sigma. We'll use sigma B a lot of times to say that it's a bearing stress, and it's going to equal force over area. But here the force and area are actually in contact. So the bearing part is that this area is bearing the load of some sort. So I mean that's still true here. This shear stress or shear force is on that area, but here we're talking about they're going to be perpendicular, or we will treat them as perpendicular, and there is a force that is being kind of distributed over some area. So there's actually two good examples in this jack here. One of them is that, you know, the jack stands are sitting out on the ground, and you know there's this area, something like this, at their base that's sitting on the ground. That area would be the bearing area in this scenario, and it's acting to kind of spread out the load. You know, if I've got, let's put our 800 pounds up here again. If I put that entire, if I didn't have the legs here, and I only just had the screw part, you know, and it just went in the bottom of the screw sit on the ground, that's a really small area. It'd be unstable, and it would put that 800 pounds on a pretty small area. So I don't know how big this, oh, let's not do that. I don't know how big this diameter is here, but I don't know, let's say that it's a 1-inch screw there. So if I did that, sigma bearing equals F over A, and I've got 800 pounds spread out over an area that's pi 1 inch squared, 1 inch, pi d squared over 4. So what is that? Let's see. Pi, well, 1 squared is 1, so divided by 4, 800 divided by 0.7854, we'll say. I'd get, oh, it's the same number or similar number. I get 1,018 psi. But which is not large, except that you got to think about this jack stand might be sitting on dirt or something like that. It does not have the compressive strength of you know, concrete or steel or something like that, so it's got a much lower strength. I don't think we have numbers for dirt. Actually, dirt is pretty complicated, so if you are civil engineering, you'll get a whole classes on dirt, soil, I guess they call it soil. But anyway, but once I start spreading that out, then this bearing stress will be much lower. So let's say that our dimensions here, let's say that we've got something here that, look, if that was 1 inch, then that's like 1, 2, 3, 4, 5. Maybe this is 6 inches, and this is let's call that 4. No, let's make it, assume it's a square, so it's just in perspective, so 6 inches also. And then let's make this little internal part, looks like that might be 1 inch, so let's make this 4 inches in here. 4 by 4, even though I drew it like a rectangle, if we looked at it from overhead, it would be a square, a hollow square. There's a cutout in the middle. So the area for that thing would be, let's see, sigma bearing equals force over area. Same force, 800 pounds. But now the area, if we did this whole rectangular base, is 36 inches squared minus 16. We have to cut out the whole. So 20 square inches. So we have 800 divided by 20. We have 40 psi. So this one is if we put all of the area on a little 1 inch circle, you know, just the screw. This one is if we did all of the force on this base here, which is much larger. So the stress goes way down. So you can manipulate your bearing stress by calculating the large area that you have spread out your force over. And so a lot of times you'll see, you know, things like these jack stands or whatever, where you're trying to spread out the force over a larger area so that you can reduce that bearing stress. There's another bearing stress that's harder to think about. There's actually another one in here that I don't want to deal with. There's, you know, this little hex nut right here is sitting on the well, not a tripod, but on the little stand itself. So there's a a bearing stress between the hex nut and the cup that it's sitting in. There's a bearing stress there that you could calculate. It's going to be higher than the base, but you could calculate that too. But another one that you might have to deal with sometimes is sort of related to this problem. So it's possible that we have this same load scenario, but the pins are really strong, so they don't shear. In that case, let's take I've already erased it. Let's just take this, I think, and copy it, and we'll deal with it down here. Okay, so let's say that the pin is strong. I don't know if I'm going to be able to erase this very well or not, but we'll erase those, and then we'll try to put them back. And we got some gray in there, and the pins go through everything. All right, so we have strong pins now that aren't going to break on us. It is possible that the pins, they're bearing on the green bar and the not the bar, but the green tube, and on the gray tube, just in a different way. But let's look at the green tube. So let's get rid of the gray tube. Gray tube is gone. We might need to, so you may not always know which piece to look at to determine, what's the worst case scenario in real life. So you might have to try a bunch of different things. We might have to see, like, well, is the bearing stress between the pin and the green tube worse, or is it between the green and the gray tube worse, or is the pin itself going to fail and shear? You might have to do a lot of what if type of scenarios in the real world to figure out what's your limiting factor. In the course, we'll just tell you, calculate the bearing stress between the green tube and the U-shaped pin. We'll just tell you what to do if we want you to do a particular thing. So what I'm interested in here is, let's draw kind of a side-ish view of one green tube, of the green tube. So the green tube was, just so you remember, it's this rectangular tube down here that's got the circle around it. So that's what we're looking at. So, it's something like this. And again, we're not going to look at let's draw it straight though. Let's not do it crooked. We're not going to look at the whole thing. We're just looking at some little section of it. So, it goes on and on. It does have some wall thickness. And it's got these holes in it. So I'm going to draw a couple of the holes. Here's one. And here's one. And they have, they're somewhat thick, right? And there's matching holes on the back that we can't see. So that pin, the U-shaped pin, is sitting and bearing on this surface and that surface, and then the ones on the back too. So that's a bearing stress. The pin is bearing on that surface. So the only problem is it's curved, right? Like if we look from this direction, so if we look at it from here, so here's our little eyeball guy, and he's looking at it from that way, then you would see something like this. And we don't know how far it goes, but there's a perfect circle here, another one here, and the pin is in both of those because we have this U-shaped pin, and the force is kind of, it's acting on this surface, and then the reaction force is on the bottom. A total, I had split it up as 400. If you look on the left side of the screen, there were two 400s, but the total is 800 pounds. So how do we deal with that? This is a bearing stress. The pin is bearing on the green tube. So it's bearing on it. I'm showing the bearing with this red arrows, the red shaded in area. The problem is it's not as easy as this because I've got the force over area idea, but the area is curved now, and I don't know if you noticed, but the force is not evenly spread on there. Let me draw it bigger. So take one, or we'll take both of these holes. So there's one, and then another one. So there's our two holes kind of isolated on their own. The force in them is largest in the center, and then it kind of tapers off until there's no force on the edges, right? So that complicates how I'm going to deal with this thing. So to simplify it, because I don't like the complication here, I'm going to do what's called a projected area. So, you know, here's the rest of the thing. I'm going to project this area, you know, this area right here, the kind of the one I've shown in the middle there. I'm going to project that area onto a flat surface. So I'm going to project the area onto, let's add a blue, because I could use a blue here. That one looks good. All right, so I'm going to project the curved area onto that line right there. And this will sort of even out the uneven distribution of force and the curved surface area, kind of average it all out. And so if I were to draw, let's see, let's copy this guy, I think. And put him over here, and then make it bigger. Okay. So, is that on your, yeah, that's on your screen. So here's the little projected area. Whoops. So it's the thickness of the tube wall and the diameter of the hole. So that dimension is the wall thickness in this case. And this dimension, let me not get those confused. This dimension is the diameter of the hole. So that's just DIA. All right. So we've got lots of little pictures here. Let's go back to this one with the green wall on it. And let's give this thing a wall thickness. It's probably 1/8 of an inch, I would guess. So that's 0.125 inches. And then we gave the pin earlier, we gave it a 3/8 inch diameter, I believe. We'll just keep that. Now, the hole that the pin is in is probably a little larger than the pin. There's some tolerance in there. Again, we're assuming everything's perfect here, so we're going to use 3/8 of an inch for the hole size also. So what we would do is sigma B, the bearing stress between the pin and the green tube, is force over area. You know, I've got this idea that the force is all spread out across there, but the total force, first of all, I have 4 of these locations, right? I've got 2 of them shown here, and then there's a matching 2 back here that I didn't draw. because they're on the back side of the tube, right? So I've got 4 forces. Each force, I'm assuming again that they are dividing up the 800 pounds equally, so each one is 200 pounds. And then the area that those forces are acting on is this projected area. So it's not the area of a circle, it's not the area, the inside cylinder of the hole, it's not any of that. It's this, the projected area, which is the wall thickness, which it just scrolled off the screen, but it's, I said 1/8 of an inch. Oh, there's 4 of these for one thing. 4 times the wall thickness times the hole diameter, so 3/8, which is 0.375 inches. So, let's see if I can get that to calculate. So we have 800 in the numerator divided by 0.125 times 0.375, and there are 4 of those, so times 4, 0.1875, which gives us 800 divided by 0.1875, 4,267 psi. So we could take that number, 4,300 psi, and check against our compressive strength. So this is, they're pushing, like the pin is pushing on the walls of this green tube in these little holes. So it's a compressive strength. And we could calculate our factor of safety. Let's do against fracture again, although this probably won't fracture, so let's use another thing. Probably this wouldn't fracture. Probably what would happen, you know, if we look at the holes right here in the middle, is it would just kind of, you know, kind of deform the hole, right? Something like that. So it wouldn't necessarily break it in half. It would just kind of deform it. So we use the word yield. So it would yield the material, or it would be elastic. Sort of like an elastic band, but we'll get to that later. Your book has elastic strength listed in it. So instead of checking against fracture, let's check this one against yielding, because that's probably more likely to happen. Things yield before they fracture, but in this case, yielding, elongating these holes would kind of make everything sloppy. You know, the holes wouldn't be round anymore, and the pins would kind of not fit right. So let's do yielding. So if we go to our structural steel and go to our elastic column, elastic strength column, because that's the yielding strength, we have a B under compression. So this is compression, meaning the pin is sitting in that hole pushing on it, so it's compressing it. The B does have a note, and it says that for these materials, unless you have a better reason, then the tensile strength is the yield strength, is the compressive strength. So structural steel has B under compression, so we're going to use 36 KSI as its compressive yield strength. So factor of safety against yielding equals our compressive, since we're in a compressive situation, bearing is compression, it's pushing against it, yield strength divided by our bearing stress. So compressive yield strength, we looked at it, it was, I didn't switch you over to seeing that. I just wrote compressive yield strength over bearing stress. Yield strength was 36,000 psi. Bearing stress was 4,267 psi. So we still have a factor of safety greater than 1, which is, we at least want that. But it's smaller than the others. 36,000 divided by 4,267 is 8.5 0.44. So still plenty. But, you know, the others were like 18 or whatever. So we would still be feeling pretty good that we're not going to have this happen to us. We could essentially add 8 times the load that we designed it for, the 800 pounds, and still be okay. So that would be a bearing stress. Now let's see what time we're at. Let's go back to shear. So there's bearing. Let's go back to shear. There are they're basically the same thing, but there's 2 other words that we might use in the shear category. So I don't even think we need to calculate those, but I want to show them to you because they kind of relate to this. So here we're just saying that the holes got deformed. They're not round anymore. They're kind of this oval egg shape. But it is possible that instead of just yielding, it totally rips these holes out of here. So there is a shear stress that's called tear out. Sometimes called punch out. And the difference is tear out like a hole tearing out versus punch out, meaning you're punching out like washers or donuts or something. You're punching them out like a cookie cutter. So these are shear stresses. And they have the exact same equation as the other shear stress, tau equals V over A. They're just special words. So tear out would be something like this. Let's just draw one sideways here. So you've got something like that green tube. There's a hole in it. There's some kind of pin in that hole. And, you know, there is a bearing stress between the pin and the hole, but instead of just deforming the hole, this whole thing, this entire thing, I've got too many holes in there, this entire thing actually tears out. So you end up with this piece coming out of here, you know, so it tears out. So if you had this little chunk, if I looked at it in 3D, whoops. I have this area here and the matching area on the back, which, you know, it's going to be hidden, but it's back there, that have to tear out. So the force, the shear force on this surface and on that surface is spread out over an area that is whatever that thickness is. So that would be the thickness of the plate. Usually we use T for that. And this dimension, which is from the center of the hole to the end of the plate. So that dimension, so we can call that maybe L. And there would be 2 of these areas. So your equation would be tau equals V over 2 times your area is T times that L distance. So it's pretty straightforward. It is a direct shear type of failure, but we call this one tear out. And punch out is the same thing, except that it's like a cookie cutter. So you've got, let's see, you've got a plate. And you've got some kind of tool, usually you're doing punch out on purpose. There's some kind of tool that you are pushing down into that plate, you know, got a force on it, and your whole goal is to punch a hole out of this thing. So you've got a little piece that comes out here, the the area is the surface area of that thing you punched out. So you have to do the perimeter of it. In this case, it's just a circle times the thickness. So again, you have the idea of the thickness of the plate that you're punching the part from, and then the perimeter is the other dimension. So it's the area, in this case, it's the area, surface area of a cylinder, but it could be any shape. It doesn't have to be round. It could be a square or completely made up shape. So it's the perimeter of that shape times the thickness, and then it is still tau equals V over A, where same V as before, but A is the perimeter of the shape times the thickness of the metal. Usually we're doing metal here, but it could be other materials. The thickness of the plate that you're punching this thing through. Okay, so that, all of this should get you through homework 3. I just made homework 3 visible, I believe. There are other videos. If you want to watch an older video of this, I do basically the same thing with different examples. If you want to see a different type of example, I think in last year's video, I worked through a web work problem specifically. So you might, if you look to the end of that one, you might have some guidance on a specific web work problem. I don't know if it's a web work problem I assigned or not, but there is one that I'm pretty sure I worked through. Okay, I think that gets us through today. We'll be back. Now, this is a weird schedule for summer. We do Monday, Wednesday, Thursday. So I'll try to do these Monday, Wednesday, Thursday. Wednesday, I don't think we will have a live stream on Wednesday. So it'll be a pre-recorded one. But Thursday and from then on, most of them should be live streams, noon to about now, 1:30 or so. And you can ask questions in the chat. You can ask questions in Discord. You can ask questions through email, or we can set up a Zoom even if you needed to for sometimes. Try to keep up with the web work. I typically leave them open for a week, but it can, if you don't do them, pretty much on track, they can start piling up. So I don't see any new questions in the chat. I'll go ahead and close our stream for today, and then I'll leave you some guidance in Canvas on what to do on Wednesday, but I don't think it'll be live. I have a camp that I'm part of on Wednesday, so I don't know that one will be live. But then we should be back live Thursday and so on. All right, I will see y'all